Okay, so this is what we've done. We wrote down our time-ordered correlation function in terms of Z of j, and then we worked out what Z of j is. Guys, just one comment. When I plugged in the value of the free path integral, I got it wrong by a factor of 1/2 in the exponent. So please correct the very last formula that we wrote down. The error is that 1/2, which is underlined in red, okay? So you can add in that 1/2. I'm going to remove the red circle. Good. And then this was the formula for the time-ordered correlator. I just plugged Z of j into the second line of this slide. Okay, good. So this is what we want to evaluate. Now, notice something. We're taking derivatives of an exponential, and the exponential has got two j's in it. What that means is, it means that just like in naught dimensions, we have to act with a pair of derivatives to get something that's non-zero. So just like in naught dimensions, need pair of delta j's for a non-zero result. So it's just like in naught dimensions. And what that means is the combinatorics. The combinatorics is just like in naught dimensions. And this is why the naught dimensional, this is why the naught dimensional exercise is useful. Okay? And having done that exercise, we can now simply write down what are the Feynman rules in 3+1 dimensions. So now let's write down the Feynman rules. And we're calculating this correlation function, phi of x1 up to phi of xn. So the first rule says you should draw n dots. This is one for each field, labeled x1, x2, all the way up to xn. And the dot labeled xk represents the field phi of xk. Then, what's the rule for the vertex? So here's the vertex. Now, where is the vertex coming from? Well, the vertex is what sits inside there, okay? So it shouldn't come as a shock to you that the rule for the vertex is the following. The vertex is given by, now it's a minus ig, okay? So you can see there's an I sitting in there, so that's new. We'll have a 4 factorial, that factor of 24 that we had. That's part of the combinatorics. And as I just told you, the combinatorics doesn't change. But there's a bit more. You see, there's an integral d4x. So now we need an integral d4x, and we need to label our vertex as living at the point x. So that's slightly different to in naught dimensions, but not too bad. Then next, if we have got a line and the endpoints are labeled x and y, then this translates into the Green's function, g of x, comma y. And the remaining rules are all things that you know from naught dimensions. So we have a factor of 1/2 for each closed line. We have a factor of 1 over q factorial for q equivalent lines. We have a factor of 1 over q factorial for q equivalent vertices. And we have a factor of 1 over q factorial for q equivalent diagrams. Okay, so that's the Feynman rules for this theory. And what you can see is, all of these latter rules, all of the ones related to combinatorics, are exactly what they were in naught dimensions. The only thing that has changed is the vertex now is labeled and we have to integrate over it. The endpoints of lines are labeled by the positions, by some positions. So we get a Green's function of those positions. And the dots that make up the Feynman diagram are labeled with the position of the field. Good. Okay, but we've got the Feynman rules. So now, just like we did in naught dimensions, we can start to write down some Feynman diagrams. So let's start off. Let's say we want to calculate the time-ordered correlation function, 5x1, 5x2. Actually, you know what? Before we do that, let me just make one comment. So the comment is the following. You've seen that the combinatoric factors are what they were in naught dimensions. And in fact, a lot survives. So for example, if you use Z of J, then you generate all diagrams. But if instead you use Z hat of J, which is equal to Z of J divided by Z of naught, then you don't generate the vacuum diagrams. Okay, so this is exactly as we saw it in naught dimensions, and it survives here absolutely unchanged. It just goes through exactly as it did. So now let's calculate this correlation function. And you know what? I am going to use Z hat of J. So I'm going to take a delta J of x1 and a delta J of x2. I'm going to act on Z hat of J at J is equal to 0. And just to be completely explicit, let me write new here as I was doing it in naught dimensions. Okay, so that's what I want to do. So that's going to be a sum of some Feynman diagrams. What Feynman diagrams? Well, to 0th order, so just the free theory diagram, I will have just this diagram going from x1 to x2. Then at first order, remember, I'm not drawing the vacuum graphs, so I'll just have this diagram. So just like in naught dimensions, except this leg is labeled x1, this leg is labeled x2, and the vertex now needs to be labeled x. And let's do one more order because I really want you to get the hang of using these Feynman diagrams. Okay, so at the next order, we've got a diagram that looks like this. We again go from x1 to x2. We've got a vertex at x. We've got a vertex at y. Then we've got a diagram that looks like this. This goes from x1 to x2. This vertex is at x. This vertex is at y. And finally, we've got this diagram. We go from x1 to x2. We can put this vertex at x, this vertex at y, and then there would be order g cubed. Okay, so we've written down this 2-point correlation function in the interacting theory up to and including order g squared. Now, there is one question that I'm sure has come to your mind. Maybe it's something that worried you, and it's a good question. And the answer is, or the question is, how do you know when you've caught all of the diagrams? So here I have written down 1, 2, 3, 4, 5 diagrams. How do I know that that's the right number of diagrams? Actually, that's a great question. And it's not easy to know. It's not like there's a simple formula that you can use to work it out. You can work it out, but it requires some nifty combinatorics, and we're not going to go through that. That would just be too much of a detour. What you will find is, especially for quantum electrodynamics, where people do like to work to higher and higher orders to calculate numbers that they really want to compare to experiment, what they will do is they will have teams of physicists working on a problem, maybe 10 or 20 physicists, all calculating Feynman diagrams. And when you get out to third order, fourth order, fifth order, you're talking of tens of thousands of Feynman diagrams. And it becomes extremely non-trivial to make sure that you've caught all of the diagrams. So I wish I could give you a really simple rule to know that you've caught all of the Feynman diagrams. There isn't one. The simplest thing to do is to start in naught dimensions, where you can calculate the value for the correlation function just by doing a one-dimensional integral. So that you can usually do just as we did it. And then you can draw the diagrams, express each diagram as mathematics, add them up, and make sure that you reproduce the answer for the integral. So that's what I do when I want to make sure that I've caught all of the diagrams. I go back to naught dimensions. So that's just another case where you see how useful naught dimensions is.